Everybody, so we're going to do the final installment on this discussion on energy, and this is really where we put it all together. So we're going to talk about really important, and hopefully once you catch on, you'll find it's pretty easy to work with. So it's called the law of conservation of energy. So we recently did conservation of momentum, so this is very similar. All right, so I'm just going to set it up for you, then I'm going to do a bunch of problems. So when you do work on a system, we've said again and again, it changes the amount of energy in that system. And we've since learned there are a few types of energy you have to worry about, right? There's kinetic energy, there is gravitational potential energy, and as we'll eventually learn, there is elastic energy or spring energy, okay? So the conservation energy comes in from if you do no more work on a system, if you leave it alone. So let's say I define a system as an object in the Earth. Then the total energy of the system remains the same. It just shifts. The forms of energy that we talk about just can change or convert from one form to another. So I can have a system at the beginning that's all gravitational potential. In other words, something's above the ground. I let it go, it falls or it rolls down or something like that. And that potential goes into kinetic or other things. Or I can use a spring to store energy and then fire something in the air where the energy can go into kinetic energy and gravitational potential. So you just have to identify the situation, the types of energies that go with that situation, and then you plug in equations and solve what you're looking for. It's pretty straightforward. Okay? So from a mathematical standpoint, what we want to say is, and this is in a reference table, well, one form or another, but I'll put the way I do it, is the total energy at the beginning of a system, of an event, is equal to the total energy after. Okay, you just got to identify the form. So if I break that down over here, I can start off with some gravitational potential and maybe some kinetic, and even I can add in the third term some elastic potential, but I won't add it here. And then at some time or some place later, I might have some new gravitational potential, a different kinetic, and if there's friction present, I'm going to throw in the Q for thermal energy. Okay, so let's just kind of look at this bit by bit, example by example. So let's say I have a ball at rest, right, rolls down a tall hill where there is no friction and there is friction. And we want to look at the energy state of the ball when it's halfway down for each case. Okay, so this is how one approach you might look at it. It's kind of like a pie chart. So we've done work on the system, and we've given it energy right here. So what form or forms of energy do we have based on the information? Well, we've got, where's the ball? It's at the top of the hill. It's assumed it's at the top of the hill if it's going to roll down, and it's at rest. So if we're at the top of the hill or above the ground, that's potential. If it's at rest, there's no kinetic. So it's all, the whole pie is going to be PEG. Okay, now we're going to look at the situation A. Put an A there. What happens as it rolls down the hill? There's no friction. Well, when it's halfway down, it's still above the ground, so it still has some potential. But since it's halfway down, it's going to have half the original, so I'm going to take my pie, split it in half, and call it PEG. I'll put a prime there to indicate it's different than the original one. And so where did the rest go? Well, it's moving, and since there's no friction, we haven't lost any thermal, so the rest is K. So if we put numbers there, and we figure out through MGH, this is, let's say, 1,000 units, then we know this is going to be 500. That's going to be 500. It's as simple as that. And if I know that the kinetic energy is 500, then I can use 1/2 mv squared to find the speed. So in the case where there is friction, so I'll call that case B, we just got to add in a third piece of the pie, which means we're going to take a chunk out of one of the other pieces. In order to know which chunk we take out, again, we take the same approach. We ask ourselves, is there PEG? Yes. What's it based on? The height. The height isn't changed by the friction, so we're still going to have half of our original energy is still in PEG. We know there's now some thermal Q, so that means we just don't have as much kinetic energy. How much the rest of the chunk is depends on a number of things. So I'll just split this like this, and let's say we just only lost a little bit of Q, and the rest is in kinetic energy. So again, if we start off with 1,000 units of potential, we still have 500 here based on a height. Let's say we get information where we have 100 lost to Q. Well, what does that leave for kinetic? 1,000 minus 600, or we got 400 for Q, KE, which is less than this. So we got a lower speed. And that's all we have to do. We don't have to worry about angle of the hill, forces, accelerations, etc. So here's another example. Okay, so we're going to have a cat fall. So it's 10 kilograms, It's launched horizontally, okay, at a certain speed from a height of 6 meters. For each meter it falls, the cat feels 10 newtons of drag. Let's determine its energy states for every 2 meters it falls. We're going to fill out this chart as it goes down, 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 where we have height, which gets potential energy, kinetic energy, and delta U. Whoops, I guess I've been using Q in the previous one, so that's what I meant there is delta U. The previous pages get confused between AP and Regents. Okay, whoops, too far here. Anyway, what I meant to say is this should be U. Okay, I was using Q, so hopefully we have not been too confused by that. Anyway, so let's do some preliminary information. Now, let's take this information and translate it. Let's take the drag part, okay, because that's what confuses so many people. So it says for every meter it falls, we have 10 newtons of drag. So, in other words, if at the beginning we have 0 drag, if we fall in right here, if we fall in 2 meters, because we've gone from 6 to 4, then we're going to have 20 newtons of drag. So I'll work that out later. Okay, so we're going to ask, do we have any gravitational potential energy at this height? The answer is yes. We would use mgh. We always use mgh. And I'm going to use a value of 10 for g. So we have 10 for the mass, 10 for g, and a height of 6. So that's 600 joules. So I don't have to write the j because I have it there. Kinetic energy. Is the cat moving at the launch? It is. So you're told it's moving. The fact it's horizontal turns out to be irrelevant. We don't care about direction when it comes to energy. That's really nice. So we would do 1/2 mv squared in this particular case. 4 squared is 16. Half of that's 8. 8 times 10 is 80. So I'll just put in the numbers here. Put the square. 4. That's 80. Okay. Is there any thermal losses? Nope, because we haven't fallen yet. And so our total energy is 680, and our speed, as a given, is initially 4 meters per second. Okay, so now we're going to look at it when we've fallen 2 meters. We've gone from 6 to 4. So do we have potential still? Absolutely. We have mgh, where h is now 4, so that's going to be 400 joules. Kinetic. Well, I can't use 1/2 mv squared here because I don't know how fast it's going, so I'm going to come back to that. Let's go to the internal energy. So internal energy, if you recall from the previous notes, is equal to the force of friction, or drag in this case, multiplied by the distance over x. Okay, so we got to work this out. We know that it feels 10 newtons for every meter. It's fallen 2 meters, not 4 meters, but 2. And then the d part is, so I'm sorry, let me step back a second, because I know this can get confusing. So my overall force is 10 times 2. In other words, I've got 20 newtons of force, and then it's fallen 2 meters, because that's my d part for the F times d. So I have 40 joules of energy lost to internal energy. Okay, so now how do I get the kinetic? Well, this is where we use conservation of energy. I'm just going to remind us off to the side, or up here. Total energy at the beginning equals total energy anywhere else. So our total energy at the beginning is this number here. That's why that was important to do at the beginning. So my kinetic energy is going to be my total energy at the beginning minus what I have at the potential and the thermal here. So I'm going to call that minus 440. So I had 680 minus 440. So I have 240 joules. So my kinetic energy has gone from 80 to 240 as we expect since we've fallen. It just hasn't gone up as much as I could ideally if there was no loss. Okay, so our total energy still is 680. Has to be. That's conservation of energy. So now if I want the speed, then I could say the speed is equal to the square root of 2ke all over m. Okay, where did that come from? Well, we've done it before. I just said ke is 1/2 mv squared. So I just rearrange it for v. So now I can take and do square root of 2 times 240 divided by 10. 240 times 2 is 480. 480 divided by 10 is 48. Square root of 48 is about 7. You can work that on a calculator, probably 6.9, 6.8. Okay, so hopefully this makes sense. What I would do now is pause it, do the last 2 rows, see if this makes sense on your own, and then see if it matches what I have. So go ahead, I'm going to fill this in. I'm going to pause it and fill it in. Okay, apparently I never paused this. So anyway, here are the answers. What we want to note is we have 200, then 0 potential. Our thermal keeps going up because we keep falling through drag. And interestingly, our kinetic is the same in the last two ones because drag is increased enough. So we go up 8 meters per second for the last two ones. And again, total stays the same throughout. Now, an important question. How would the drag, suppose instead of falling down, instead of being projected like this, the cat had slid down a frictionless chute. How would the values in the chart change for each given height? Well, potential energy, gravitational, only depends on height. It doesn't matter how you get there. So PEG would stay the same because path down doesn't matter. Okay? Now U would be 0 because I said frictionless and we're going to assume no drag. Okay? Therefore, at each height, the kinetic energy and the speed would be greater than before because we're not losing any energy to thermal, and the path down doesn't matter. That's the important thing. That's what makes working with energy so easy. You don't have to worry about those angles. Okay, so let's look at graphs. How do each of these change with height? So I'm going to do two plots on one graph in different colors. Let's start with PE with height. Okay, so for height is 0, we have no PE. As the height goes up, it goes up linearly because we know PEG is proportional to H. So what happens to kinetic energy? Well, remember, the total energy has to stay the same. So when potential energy is at the least, our kinetic energy is going to be at the greatest. And then when potential energy is at the greatest, our kinetic energy is going to be the least. So it's going to actually go down like this. And what's really important is what stays the same. So I'm going to do it a third color, is the total energy. So total energy stays the same. It's just always going to be the sum of these two at any given point. So if this is, let's say, 400 and this is 100, our total is 500. If I choose a different spot, let's say right there, they're both 250, such they add up to 500. Okay? So as one rises, the other falls. All right, so I'm going to stop there. Okay, what I want you to try to do on your own is the next problem. Okay, I want you to use conservation of energy to try to do these rankings, and then we'll talk about them in class. Okay.